Thank you, Tariq. Hello, everybody. First, I'd like to thank the ERSEC 2020 for inviting me. I'm happy to be here with you guys. And the title of my presentation today, I changed it slightly compared to what is announced in the conference pamphlet. Here it will be about the material design for energy conversion using solar visible light. The core of my presentation is not changing. It's still focused on material engineering and design, and to show how this will promote high energy harvesting and also the energy conversion. Here, the energy to be harvested is the solar spectrum, and the conversion will be mainly in transforming this light to electrons, helping semiconductor material to achieve efficient water splitting and hydrogen production through what we call local surface plasma resonance. And I will explain this during my presentation. So first, one has to be aware that the challenges facing the clean energy development is very high and is very challenging because the industry working in the fossil energy production, they are putting together a lot of technologies and innovative solutions to be able to get more profit of the fossil energy. So here I share with you the prospect of a cost profile of oil production, for example, for 2035. And you can see how many profit they are putting by just changing the way how they do the reservoir exploitation. For example, just for instance, they are using what we call EOR, enhanced oil recovery. It's another method to continue using for conventional reservoir and to increase the efficiency by 70%. They are also using offshores, and they are using deep water wells, and they are using also shallow and so on. So there is too many technologies and many ways to continue getting cost-effective production of fossil energy and continue producing them. So I understand that the industrial that are aware of the impact of greenhouse gas emission to our health, but they care more on how they continue having a benefit of the industry of energy. So it is not easy to take a clean energy step in the comparison with the conventional fossil energy, only if we make the business case. So this is show that fossil energy won't be depleted any soon, even though they are teaching us that this is that fossil energy is shrinking, but they are developing also different technology to get more benefit of it. So the challenge for the clean energy development now is two things, because the development of clean energy also introduces CO2 emission. So we have to be much more efficient in terms of mitigating CO2 emission. And also at the same time, we have to develop cost-effective clean energy to attract investment in this domain and to converse also the traditional industry to convert or to make the smooth transition to clean energy. So here in this slide 3, if we talk the clean energy, you have to know who is actually making more investment in this technology. So most of them, as you can see from this slide, is the Western countries and developed countries. They are putting more money in developing renewable energy, even more than China and the undeveloped country. So what is the reason? So there is two main reasons. This is one of them is because they are not mastering fossil energy or they don't process it. But in the same time, they think that introducing clean energy will create momentum momentum that will take their economy step upward and create more jobs and more opportunities. So, and also in terms of technological wise, it will take them to another step compared to other countries. So we, again, it's very difficult to put in place in this technology in just undeveloped country or in the country that they don't have enough technology to take this technology forward. So again, we need to increase the investment of this technology, especially in the countries that don't possess fossil energy. So, for instance, if I show you now the hydrogen production and the different routes used to produce the hydrogen. So again, it's too bad for us. It's still fossil energy is the source of producing clean energy hydrogen. So, for example, there is 50% coming from natural gas, 30% coming from oil, and 18% coming from coal. As fossil, they are all, industry that it is emitting greenhouses footprint. So it's and also if you see water electrocatalysis, for example, accounts only for 44%. It is not sufficient for us. So why is the case? Because the business case is not there using the water electrocatalysis. So now the challenge is, in one hand, we have to develop water photocatalysis, highly efficient because it will show less carbon footprint, and hopefully because, with low cost, because it will use unlimited sunlight energy. So in this slide, I show you the principle of the photocatalysis fuel cell. So if you see, it comes always with the semiconducting material and a counter electrode. And the impinging light from the sun should actually produce enough energy to split the water molecule. If you see the mechanism in the middle here, you can see that actually when the impinging sunlight will hit the junction of the semiconductor, which will excite the electrons from valence band to conduction band. And this conduction band will be overwhelmed by electron, or we have enough electrons in this band that it will be a site of reduction of water molecules. And this will lead to hydrogen production. On the other hand, the holes remaining in the valence band will be having lack of electrons, so it will be site of oxidation, and here it will be where we will have the oxygen evolution reaction. So this is possible only if we can provide energy above 1.233 eV. And this is not much semiconducting materials are having these properties, or they have these properties like, for example, CDS and CDSE. They have this actually possible property, but they are unstable and they are also prone to corrosion. So what is the remaining materials? That they are wide bandgap semiconductor. For instance, the one that strontium titanate is very known as a photocatalytic material, and titanium dioxide also in anatase form of it, it is very known to have very high photocatalytic activity. So, but the wide band gap of titanium dioxide is about 3.2, which yield to only absorption of UV light, which accounts only for 4 to 5% of total sunlight, which is not sufficient to produce a highly efficient photocatalysis reaction. So another problem, even though if we collect light and we have too much load collected, most of them, you see here in blue in the solar absorption, if we don't put any enhancing catalytic metal, they will be, converted to phonon, making thermalization, and most of them will be completely lost. It's almost 30% of the visible light absorption. So only available now for this instance is only the, here I put in yellow, which actually invisible region, accounting also for UV, which only 30%. So this is the idea here, is to be able to also use the full spectrum of solar energy. It means UV and visible light without losing irradiation due to thermalization and other aspects. Or, for example, here we have some not absorbs, we have some extraction losses due to just geometry of the materials. So this is why we have to think about to develop critical technologies to achieve the use of the visible spectrum of solar energy to achieve efficient water split and heterogeneous production. So how to do that? So we have to first improve the solar energy collection efficiency from the semiconducting catalyst. This has to absorb and utilize the visible range of sunlight. So we have to find the way how we can extend the absorption light for semiconducting material to visible region. In the same time, we have to be able to actually load the semiconductor material with something that have like LCPR material, metals, local surface plasma resonance materials, as photosynthesizers to generate hot electrons by plasma resonance. And these hot electrons that are generated, hopefully they can be injected to conduction band of the semiconductor, and then it will be used for a continuous water splitting. So I will give a word here about localized surface plasma resonance. So what is about? First, the surface plasma resonance is happen when we shine the metal with the electromagnetic wave. When we shine material surface with magnetic wave, we have a cloud charge, electron cloud charging moving on the surface. But now if it happens that the size of the metals is below the size of impinging wavelength. So this will make the particles of metals will oscillate. And depending on the frequency of the oscillation, if it is the same as the particle size, we will have whether we have random oscillation or we'll have a local surface plasma resonance, because we have the same frequency from the particle and the same resonance particle, and also the same from the light. So this oscillation will create the hot electrons cloud here, and if it is put next to dielectric like semiconductor material, it will inject this hot electron to a conductive band, and it will make a more charged electron in this band, which is actually a side of reduction of hydrogen molecule for hydrogen production. And here we will have more lack of electrons to be site of oxidation for oxygen evolutionary reaction. And so it means that most of the LCPR will be providing these hot electrons to enhance actually the photocatalytic activity. So the idea here is to first of all to make a very nice geometry and design for material and load it with titanium dioxide, then with gold particle to make very good composite materials that can make light trap the visible region, the solar spectrum at very wide range of spectrum, and at the same time it will make the LCPR to provide with hot electrons to conductive band. So here the design of our metallic photonic catalysts. So we do it in a clear room, and there is many steps. Here the steps E, B, C, just to make a template in D, and this template will be loaded with titanium dioxide here in green, and then with gold particles. Here we have techniques used for each step of fabrication, and by doing that, we were able to lead a device with this shape, like cup-like shape, and it is homogeneously distributed, and even this shape is like a tube or cylinder that will actually, with capillary, can attract water molecule. This is the first. Second thing, it will, when the water will be in contact with titanium dioxide inside the wells here, these cups, it will use the LCPR from gold. This is what we're supposed to have to actually continue splitting the water molecule. And this is the device view in 3D. And this is how it looks like. We show you now if what is the light absorption of this material, what is the photoresponse, and at the same time if there is any LCPR activity. So here I will show you the light absorption and the photoresponse of the device. You can see here that we here for different thicknesses of gold particles to optimize the size of the particles. So ranging from 20 to 30, and at the same time used in flat silicon and also in shaped silicon. And we found that the like cap-like structure that we have with 20 nanometer of say thickness of gold have very higher photoresponse. We put here the normalized photoresponse, based on the thickness of the samples we have, and we have the maximum photoresponse laying in the visible region, here between 450 to 780. We have the maximum actually at around 600 nanometer, sitting exactly in the visible region of the solar spectrum. This is very interesting. This photoresponse shows how many how many light will be absorbed to be actually changed on electrons. So now let's see, we are able to see that now photo absorption extended in the visible region. So how about the LCPR activity? So to check that, we use the cathodoluminescence. This consists of shining our structure and see if there is any antenna, and to correlate observing antenna that they are signature of LCPR activity and different in the interface between the gold and titanium dioxide, and make it in correlation with the wavelength. So here we see in visible light, we have this antenna appearing everywhere in the intersection between gold and particles and the semiconductor material. And this can be shown, can be translated in color code very easily. And you see in all visible region, we have this antenna structure showing very high activity of LCPR. So basically, now we are able to extend the absorption in visible region, and at the same time to enhance the LCPR activity in this device. To further study the efficiency of this LCPR, we first try to observe this phenomenon at very high resolution using energy electron loss spectroscopy inside high resolution transmission electron microscope. And here our shape of our device, and you can see that different energy windows, we were able to trigger this LCPR at different position of our fish hook-like structures, showing that first our design is efficient because it triggered LCPR at different energy windows, which is actually coherent with photo response in the visible region. And when we reproduce similar structure using finite domain time difference simulation, we're using different geometries of excitation of electron field, and we observe the generation of exactly the same LCPR activity, and we have the coherence between two simulation and the experiment. This is show now the high active, why we have photoresponse at visible region, because LCPR existing at very large energy windows. Now, if you want to qualify this energy region and to see how much this is interesting for our for water splitting activity, we can measure what we call the Q factor, which actually describes the local field enhancement. So how many electrons field we are producing in the interface between gold and the titanium dioxide, and this cloud is related to electrons movement and oscillations. We can show that we have a Q factor that we are producing with our shape, which actually fish hook-like shape, is very, very high compared to even nanoparticles as described in literature. So finally, we are able to show that LCPR are enhancing highly the production of the clouds of electrons that they can be injected the conduction band of the semiconductor, leading to highly high activity of water splitting, they yielding to good hydrogen efficiency, production reaction. So I come to a summary of my presentation. So I hope that I convinced you that we are able to design new device using LCPR material and semiconductor material, and we were able to extend the absorption from UV only to whole visible light. And the design of our structure is help us to make light trapping. So, and this is make high photoresponse in the visible region. And this is due to local surface plasma resonance activity, as we showed. And we also showed that this LCPR has very high Q factor compared to what is admitted in literature. And this photocurrent induced will provide with hot electrons to be injected to conduction band of semiconductor, allowing continuous water splitting. So by this, I thank this person who participated in this work, and thank everybody for his attention. And thank you very much for this presentation.